Hey, stats class, let's look at a homework example from 8.3 where we're doing hypothesis test now about means. So I know this is a hypothesis test about a mean without seeing anything down here because the sample statistic they give me is a sample mean, right? But it says test the claim the population of student course evaluation has a mean equal to this. So that is the way that, again, another way that I know this is about means, just that statement right there. All right, the setup would be because the mean is equal to this, it's not giving a direction, greater than, less than, not equal to. It is strictly saying equal. So that's going to be the null hypothesis. And so when they're just saying equal to, the alternate is going to be not equal to, because again, a direction is not implied. So we would just use a two-tailed test. All right, this is about a mean. So when you go to your sheet this time, you got to make sure you pick one. We don't deal with this situation in our textbook. Just it's not realistic to know the population standard deviation and then not know the mean. Again, if you're doing this, you're estimating the mean. And somehow I know this, but I don't know the mean. But the standard deviation, the formula that we learned how to get standard deviation, we had to know the mean to get it. So it doesn't make any sense to not know the mean, but to know the standard deviation. So it's just not practical to use that, so we don't see that very often, other than a stats book. So we're doing the T statistics here. But we need the sample mean. I'm just going to label the things that we need. Sample mean, we need the population mean, we need S, the standard deviation, and we need the sample size, which is N. You could just put N there. Alright, so just going through on the problem. X bar is the sample mean, so that's the 4.11. Alright, the population mean is what I set up here, but it's test the claim. The mean is equal to 4.25. That's the one that goes here. But if you get it right in the homework, it's the number that's beside that. It's 4.25 all the way through there. That's the population value. Standard deviation of the sample, that's the 0.54, and our sample size was 85. Alright, so again, just like with the test statistics in the proportion section, I need a parentheses up top because I need to do this subtraction before the division. So the only way subtraction beats division in the order of operations is if it's in a parentheses. So parentheses, sample mean minus population mean, close the parentheses, divided by. Now here we need another set of parentheses around this because S is divided by the square root of N. So all this needs to be in a parentheses as well. So parentheses S divided by SQRT for square root, open that parentheses, and then the sample size N, close that parentheses, close that parentheses, and then you can hit enter. So there's our test statistic. All right, they want it to 2 decimal places, so I've already got it rounded to 2. But remember, you can use this to go up or down if you need more, or down if you need less. But if you go down to how many decimal places you need it, then the spreadsheet's going to round it correctly for you, and you don't have to worry about rounding it. All right, so there's my test statistic. All right, the p-value. Now, what you got to remember is this is no longer the z distribution. You're now in a t distribution. So when I calculate the p-value, I need to use equals t dist. All right, now x, the number that it takes in, it will only take in positive values. So notice it's negative 2.39. It's going to take in, I'll put in positive 2.39 because, again, it only takes in positives. The degrees of freedom is 1 less than the sample size, so that's 84. And then for the tails, I'm going to put 2 because it's a two-tailed test. All right. If I put 1, I'll show you what happens. If I put 1, it gives me the 10% p-value. But because it's a two-tailed test, if I put 2, it doubles that and gives me the 0.19. It's basically, again, when it was, let me go back to 0.1. There's more decimal places. So doubling that number is the reason why it's not 0.2, it's 0.19. But when I switch it to a two-tailed test, it doubles that p-value for me. So that's a 0.019. Okay, so that is a two-tailed test. So do make sure that when you use that you just just leave that off. If this were a one-tailed test, like strictly greater than, then what I would have to do is, if I were in the right tail, I don't have to do anything because the 2.39 would have been positive, and it's expecting a positive number. But if this had been a left tail test, so remember 0 is the middle, that would have been negative 2.39. If this had just strictly been left tail test, I'm not going into the right tail. I'm just going into the left tail. So what's basically happening is that we are flipping it over and using symmetry and doing a right tail test with a negative number anyway, and that would have been the p-value. The area into the left tail below 2.39 is the same thing as the area that would have been in the right tail above 2.39. So that's the reason why it only takes in positive. It just allows you just kind of mentally flip it and use symmetry to come up with the p-value. All right, we always compare the p-value to alpha, or we do initially once we're getting the hang of it, hypothesis testing. So alpha is 0.05, the p-value is 0.019, so the p-value is less than alpha. So when that happens, we reject, and if we reject, it's because there is sufficient evidence. And then this is a weird the way this is worded. This is the alternate hypothesis, right, which is not equal to, right? So the equality of 0.25 is not correct. That's another way to say not equal to, which is what the alternate hypothesis says there. So it's a weird way to word it, but that is the correct response.